will immediately start testing our man-made receptors for their ability to instruct real T cells to kill cancer over and over.
The experiments on T cell engineering really failed in the beginning. We could introduce genes in many cells, but not T cells. We didn't understand why. Today, in one afternoon, I could teach a high school student how to introduce any gene that they want and any T cell that they want. They even laugh when they don't understand when we say how long it took to perform this thing that today is done so easily. But this is how all of this started. And then finally I understood some of the restrictions on that process, and genetic transfer started to work.
The idea was to modify patients' cells and to add new properties to them.
Well, this is my attempt to represent on 2 dimensions all the components that had to fit together to come up what we now call CAR therapy. And it all begins about over 25 years ago with really gene transfer into T cells. At the same time, we had to develop receptors, synthetic receptors, to retarget and reprogram T lymphocytes.
In Greek mythology, a chimera is a creature that fuses together the head of one animal with the body of another. Similarly, a chimeric antigen receptor, or CAR, joins together a part of an antibody with part of a T cell receptor.
For CAR T cells to be effective, they should not only kill, but multiply as long as there is remaining target to eradicate.
And so finding the target is another critical aspect of this. And here, we identified a very important molecule for the history of this field that is called CD19. And CD19, this is the molecule that other programs eventually decided to pursue, and we chose it because it is expressed on most leukemias and lymphomas, and also because it is expressed on a limited number of normal cells.
So, everything was ready for a crucial experiment.
We did an initial experiment in mice where we took human tumors in immune-compromised mice, and we treated those mice with T cells that were targeted with a CAR to the prostate target, so these were negative control, and were targeted to CD19, which was the treatment group. And this was before smartphones. It so happened that my wife and I had to go on vacation to Ireland when the first cohort of mice that were treated this way would either develop disease or not develop disease, because it was a very reliable model. And I still recall that I had 2 cages with 5 mice each that were the control group, and 2 cages with 5 mice each that were the treatment group. And my wife told me I was not allowed to call the lab while we were on vacation. And so I remember coming home from the trip and calling up the lab and asking the technician what happened to the mice. And she said, well, a whole bunch of them died. And I said, well, which ones died? The control ones or the, and she couldn't remember. And so we got back to the apartment and I left for the lab immediately that night, and I found 2 cages of 10 healthy mice, and none of the control mice were alive anymore.
This was the first time that they could actually demonstrate that modified T cells could fight tumors. Clinical trials were ahead.
Соня сделала очень разное. Первый раз, когда мы учились, у нее были волосы, и вот они стали отрастать, и можно было делать такие прически классные. Соня, какой инвалид уже, да, ему раненый физически, потому что ребенок, который мы едем на пункцию, она говорит, ура, мы едем на пункцию, слава богу, она под наркозом. Вот. И я, который, значит, постоянно как на приговор на эти пункции, потом ты ждешь выходные, не можешь позвонить, ну, неудобно обследования к обследованию ждешь вот этого вот приговора. Когда меня спрашивают там в больнице, как ты там держишься, как ты это переносишь, я говорю, не знаю, с помощью Сони. Ну, потому что кто кого поддерживал, это был большой вопрос. И она меня утешала там в любом состоянии. У меня вот это вот все начинается, трясучка, она меня успокойся, не нервничай.
Но люди не понимают, что КСМВ, ты не знаешь, но для лейкоза все решат записать, я начинаю жить с ним.
To prepare for that stem cell transplant, I did, again, a couple weeks of very intense chemotherapy and radiation. And during that time, while I was preparing for the transplant is when I met Dr. Matson, and he said to me, you know, Camille, if this transplant doesn't work, there are other options. And I said, like what? And he said, there's something called CAR T-cell. But at that time, I wasn't really thinking too much of it because I believed that the stem cell transplant was going to be my cure. So that's when we went ahead with the stem cell transplant in July, and I remained in hospital for another month, a full month, during the pandemic. So at that time, I had no family or friends visiting me, and I was unfortunately in a little room by myself, and I only saw the nurses and the doctors, which was very hard. I was very unwell. It was very, very hard to recover after transplant. And then one morning I woke up and I had some neck pain, but I didn't think anything of it. I thought, okay, I slept funny. And then the next couple of days, the pain started to move in the body and it became very painful, and I knew something was wrong. And they admitted me to hospital, and the transplant team from Princess Margaret came to tell me that my cancer was back and it was aggressive.
To succeed in innovation requires, first of all, creativity, of course, skill, probably some luck, but most importantly, resilience. It may require rejection of authority. So now we're not just talking about creativity, but rebellion, or even subversion. Others too added their mark along the way. Martin Luther King, Che Guevara, Friedrich Nietzsche, and not to forget, of course, the arts and the artists. The Beethovens, the Picassos, and many other iconoclasts. All of this goes into defining who a scientist is and what work he or she may produce.
Science has three main purposes: to understand, to predict, and to modify, some might say to control. The practice of science is based on analysis of observation, analysis of experimentation. In fact, we tend to not allow ourselves to speculate too much. And I wonder sometimes if that has a negative impact on imagination. This is why access to art is so vital for scientists. The artist doesn't have to be reproduced by others to be validated, unlike the analyst or unlike the scientist. I think creativity has been an essential component of the emergence of CAR T cells.
I was fortunate to have encountered rebellion throughout my education. And my family had survived 2 world wars in Ukraine. My father had tricked the Polish Communist Party to escape to the West. My grandfather had fought illegal internment in Canada, in camps in the mountains and in the north, which eventually killed him.
My father, when he got out of the prison finally, he became a very strong socialist and a strong advocate of social justice. And he went on for the rest of his life doing things like with unions and working for poor people. And we believed in complete honesty and perseverance. And that's, I think Michel got some of his perseverance from that.
In 2011, the New York Times asked me, so what is it you do? And my answer was, we create living drugs. Yes, the engineered T-cell is the medicine that grows in the body as long as there is cancer left to fight. So CARs are synthetic molecules that accomplish multiple tasks once they are introduced into T-cells. One of them is to target the cancer, meaning allowing the T-cell to recognize, to see the cancer, and then to bind, to latch on to those cancer cells. The next thing that the CAR does is instruct the T-cell to react against the cancer, actually to get angry. And when the T-cell gets angry, it activates genetic programs to kill those tumor cells. And the third very important component of the CAR is to expand the different functions, the different molecules, if you like, that a T-cell can potentially use to fight the cancer. And it also expands the persistence of the T-cell, because the T-cell, being a cell, is alive. And this is what's very unique about this medicine.
And it's like trying to say, like, I want to build a car, not a T-cell car, but a real car. Well, what if I just put a more powerful engine in? Well, if you don't have the proper steering, you don't have brakes, you don't have the ignition key, it's very hard to make the car work. Michel was one of those people who, already back in maybe the early 1990s or the late 1980s, was already starting work on the tools, the foundational pieces like the ignition or the wheels, the tire support, the brake system. He's working on those pieces already, working on the vectors, the modes for delivering the genes to the cell. So that work, Michel did important work there. There were several other groups he contributed. There's people like Carl June, there's people like Zelig Escher, and even Dusty Miller, if you go way back in the vector days, Richard Mulligan, Gary Nolan, and all of those pieces have slowly come together, and finally they passed this hurdle of functionality. So you stuck the key in the ignition, the thing worked.
I think that the reason why it's car, because it can be improved to a better level, and it can do more things faster and better.
The cars in real life, what they'll do is they'll drive, they drive around. The molecule cars, what they'll do is they guide the T-cells, so they kind of drive the T-cells.
This is first generation, second generation, and the future.
A key innovation pioneered by Dr. Sadelain's lab was the addition of a special molecule, co-stimulatory, to an early CAR prototype. Without this molecule, the genetically modified cells petered out quickly. With it, however, they survived in the body for months, Dr. Satterlane dubbed these newer models second-generation cars.
Then we need to develop manufacturing. How could we bring this to patients? There was no industry that was able to provide the service, so this is something that we had to undertake ourselves. And so this is where the very critical science of cell manufacturing becomes critical and takes central stage. And this is, of course, what my colleague Isabelle here accomplished so amazingly right here at Memorial Sloan Kettering Cancer Center.
I started from scratch. They gave me the keys of the laboratory, and I had half a technician who I was sharing with Michelle, and I was asked to basically develop all the infrastructure that was necessary in terms of the manufacturing of the cells, but as well as setting up the regulatory documentation that is necessary to be able to control the manufacturing of the cells, and also develop the various tools to genetically modify the cells.
From that point on, Dr. Satterlane was in charge of the theory and Dr. Riviere of the practice.
We had that proof of concept in the early 2000s, and we were able to publish this seminal paper that allowed us to basically go to the next step, that was now devising and building the process that would allow us to now infuse these T cells in the patients.
CAR therapy has changed the concept of cancer treatment. Blood is taken from the patient only once, and the blood cells, after modification, are returned to the patient.
We put the cells into a bioreactor. So in total, the procedure takes about 10 days from the time we take the blood from the patient to the time where a large proportion of the cells are now expressing the CAR.
The first clinical trials in patients with acute leukemia began at Memorial Sloan Kettering Cancer Center in 2009.
When we started doing clinical trials, and we treated the first patient with B-cell ALL that had a significant amount of disease. But I had to get a bone marrow sample to find out what was going on. And we couldn't find a single tumor cell in there 10 days after we treated him with CAR T cells.
Our first adult patient treated, was on the front page of the New York Times in 2011, and he gave his name as Bill Ludwig. He had been a Marine and a retired prison correction officer. And we treated him, and he said, he didn't think he was going to make it to Christmas. He had already paid for his own funeral. So he went in remission and came into our clinic and said to the clinician, David Porter, says, guess what? I bought an RV. And he and his wife went on retirement cruise on an RV. And then we had, in 2012, our first pediatric patient, and that was Emily Whitehead, who was also on the front page of the New York Times. And almost died both from leukemia and then from cytokine release syndrome. But on day 23, we did a bone marrow aspirate, and she was in a complete remission. And it was just an amazing thing. She went home. The firehouse, there was a fire department came in. She's in a very small town in the middle of Pennsylvania, and they brought her dog out to her and dropped in her lap. And you could see that. It was an amazing, touching story.
The youngest patient to actually come to our trials, I remember, is only 4 months old. Because he received our T cells, and so many years later, he's still alive. I cannot imagine young parents have young children with terminal disease, how they feel. But I know how I feel when we know our therapy works, and up to date, the small children is still alive. How it feels is really rewarding.
In New York City, even in the buses and in the subway, a latest breakthrough in cancer therapy. You are the treatment. You is your T cells, your immune system, with the help of the CAR molecule, is instructing your immune system to go and find and kill the tumor. This is the breakthrough of immunotherapy.
In other words, we are really experiencing a revolution which will impact the way by which we treat cancer and we cure cancer.
I think that cell therapy and human cell engineering are subversive. They question the medical order and the monopoly of chemicals over the world of drugs.
The advent of CD19 CAR therapy challenges established models of drug manufacturing, distribution, and administration, as well as pricing and reimbursements. It has set into motion a tsunami that will eventually engulf all areas of medicine. For the first time, the pharmaceutical industry tackled the challenge of providing cells, CAR T cells, on a global scale.
This is kind of like in graduate school for CAR therapy. It's a whole new way of thinking. And Novartis took the initial step, and what I'll say is that was a catalyst for many, many other groups, investors and other pharma companies, and small biotechs, to make the move to focus on this therapy. So now, instead of just a couple of small companies, some academic centers, you have that it's global. It's, you know, China, Europe, US, across the world.
Strange to recall how 20 years ago people had said this was a crazy idea. How 15 years ago they had said this could never work to treat a mouse. How 5 years ago they said that even if you conducted a clinical trial, this simply could not work.
In 2017, CARs hit the road. The U.S. Food and Drug Administration approved the first CARs for clinical use. These are second-generation CARs specific for CD19. Today, hundreds of laboratories are implementing CAR therapy in different countries, from the USA to Australia, from China to Canada.
I didn't think I would survive the chemotherapy. But during that time, I was